academic year was an NSF postdoc and University of California's president's postdoc at Berkeley. Those are pretty good accomplishments, and will return to Berkeley in the fall of this year. So I will turn it over to him to tell us all about his mathematics.
Yeah, thanks. And yeah, going to Berkeley, I just had to get these for construction. Yeah, so yeah, just want to thank the organizers for the invitation to speak, as well as the morning speakers for their wonderful presentations. Now, I don't have as much experience as them, or as many enlightening things to say, so I'll talk about some of the math that I like. So I come from kind of homotopy theory and algebraic geometry, and I want to talk about some results in these areas that I think can be appreciated by lots of different people. So the title is Reconstruction in Algebraic Geometry. And the rough plan for the talk is I'll start with some motivation. And don't worry if you're not a huge fan of algebraic geometry, because there will be things which are not about algebraic geometry in this motivation. And then I'll talk about kind of one of the fundamental invariants that will come from this motivation, called the étale fundamental group. Then I'll talk about some conjectures and work in this area that's called Abelian geometry. And then at the end, I'll talk about some recent results, recent reconstruction results. So most of this will be a survey, and only in this last part we'll mention some things that I was involved in, as well as some things other people were involved in. Okay, so putting the slide. Okay, has everyone got this down? If you haven't, sorry. So the first piece of motivation is on reconstructing fields. And I'm going to use this to motivate the term reconstruction and what I might mean by reconstruction. So there's a theorem in number theory by Neukirch in 1969, and Uchida extended the results in 76. That says the following. So the slogan is that number fields are completely determined by their Galois groups. So the setup is I'll have K and L number fields. So these are just some finite extensions of the rational numbers. And K bar and L bar separable closures, or well, algebraic closures. And so whenever I have a group and a Galois extension, you can look at the automorphisms of that field extension that fix the ground field, the Galois group. And when it's the separable closure, you have the absolute Galois group. And what this theorem says is that there is a bijection between, on the one hand, isomorphisms of profinite groups. A word on this in a second, between this group of automorphisms of k bar fixing k and automorphisms of L bar fixing L. So this profinite, if you're not familiar with it, yeah, somehow the point is that these groups have a natural topology on them. And it's a compact Hausdorff totally disconnected topological space. Another way of saying that is you can write it as a limit of its finite quotients. So that's why it's called profinite. And what that is just saying is that this Galois group of the closure, the Algebraic closure that fixes the ground field, you can write that as a limit of Galois groups of the finite subextensions. But it's important that there's a topology here. This is something kind of important in algebraic geometry. So there's a bijection between isomorphisms of these profinite groups on the one hand, and on the other hand, isomorphisms of fields. Say K bar, L bar, that fix, that send K to L. So what does this mean? This means if I have a number field, then its Galois group as a group with this topology completely determines it up to isomorphism. So you can reconstruct the number field from this. Now, because it will be useful later, let me also give an alternative formulation of this. So alternative formulation. One way of saying this is if you look at the set of isomorphisms from K to L, that has a natural map to isomorphisms from this group to the Galois group of L. And it's not quite that this map is a bijection, but that it's a bijection as long as you mod out by conjugation, because somehow there's a choice involved of the separable closure. So there's a bijection where this side means you take isomorphisms of these profinite groups. Okay, let me just abbreviate notation like this and not write the extensions. Modulo conjugation, where you're acting by conjugation on the second term. Okay, so the slogan is just that you can reconstruct number fields from their Galois groups. So you might ask a natural question here, which is, what about in positive characteristic? Can we do something like this? Yeah.
One question about the left-hand side of this bijection. Is it like those profinite groups which happen to show up as absolute Galois groups, or do we also know that any profinite group is the absolute Galois group of a number field?
No, I think not of a number field. You can always, yeah, I think if you're given a profinite group, you can always write it as the Galois group of some field, but of arbitrary characteristic, but you can't guarantee necessarily that it's a number field, I think. Yeah, so it's just saying, if you have, something that arises from number field, you can reconstruct it, but it's not, yeah. Somehow it's also not in some sense, the proof's not really constructive. It doesn't exactly tell you how to how, like, if you're just given this data, how specifically do you find the field? So there are results in that direction. Okay, but so you might ask, what about in positive characteristic? Is there some problem there? And it turns out there is a problem, but there's a generalization of this. So let's look at a finite field with q elements. So q will be p to the n. Then if you look at the Galois group of fq, well, all of the finite extensions are just fq to some ith power. And these are cyclic, so the automorphisms of this are generated by the map that sends an element to its qth power. So what you find is that this is some limit of groups C mod I, also known as the profinite completion of the integers, which you can also think of as a product of the p-adics for in P. And this doesn't depend on the characteristic or what Q is. So certainly such a result, at least in a simple statement like this, can't be true in positive characteristic. But there is a theorem of Florian Top from the early 90s, which is that the conclusion of this Neukirch and Uchida theorem also holds for infinite fields that are finitely generated over their prime fields. So what does this mean? These all have a particular form. They're K adjoin some number of function field variables, where K is either a number field or FQ. So in positive characteristic, it is true as long as you have some additional function field variables. So why I want to kind of state these results is somehow there's some seemingly kind of simple cases of fields where you can attach some algebraic invariant to them, which turns out to completely determine the isomorphism type of these guys. And so you might wonder, if you're an algebraic geometer or you just know some algebraic geometry, you might wonder, are there results like this for higher dimensional varieties? Can I take some nice algebraic variety, associate to it some combinatorial invariant, like a group, or maybe something more complicated, and that will completely determine the isomorphism type? And so that's the theme of this talk. And so the answer is, turns out yes, in many cases. And so some of the results I think are kind of striking, but beyond being just striking results, they also lend to new tools that allow you to access a number of different areas of math. Any questions so far? Okay, so I want to give some motivation. So if you don't love algebra, this other part of the motivation is going to be about the geometry of manifolds. So if you tuned out, it's a good place to tune back in. So there's some motivation about some other reconstruction theorems. And part of why I want to say this is because if you want to try to generalize this to higher dimensional varieties, you need to know what to replace this Galois group by. And this discussion will inform that. So there's a theorem in about hyperbolic manifolds called, well, I think usually it's called just Mostow rigidity, but I think Gopal Prasad had a pretty non-trivial contribution to this, so I'll include his name too. So Mostow originally proved what I'll state, and Prasad generalized it, but I just don't want to complicate the statement, in the late 60s, and this was in the early 70s. So n, which is our dimension, will be bigger than or equal to 3, and we'll have x and y connected, compact, hyperbolic n manifolds. And the result can be stated in a few different ways. Let me give the maybe usual statement. So the right notion of isomorphism between such thing is an isometry. So the result says that isometries from x to y, well, one way of saying it is that every homotopy equivalence between x and y is homotopic to a unique isometry. How I'll state it this way is there's a bijection between isometries from x to y and homotopy equivalences from x to y. But then I better take only homotopy classes of homotopy equivalences. So maybe that doesn't look so much like this type of result right now, but there's a classification theorem for these hyperbolic manifolds, I think called the Cartan Hadamard theorem. And what it implies is that the universal covers of x and y are some Euclidean spaces. So these x and y, they're connected. They have some fundamental group, but then they have no higher homotopy groups because the universal cover is contractible. So another way of saying this, because these are what in algebraic topology we call k-pi1 spaces, meaning they have homotopy groups only in degree 1, is these are the same as isomorphisms between pi1 x and pi1 y. But, well, you know, these groups are kind of only, you know, you need to choose a point or talk about base point preserving maps usually. And if you don't do that, you have to mod out by conjugation. So these are what I'll also call outer isomorphisms from pi1 x to pi1. So what this says is that the fundamental group of one of these compact hyperbolic n manifolds, it completely determines the isometry type of the manifold. So you can reconstruct. I mean, again, I think it's maybe not, well, I think the proof in this case can be made somewhat constructive, that you can kind of say how to reconstruct it. But at least from this formulation, it's maybe not obvious how at all how you would reconstruct it. So maybe the idea that I want to get across, the idea is maybe if we want an algebraic geometry type reconstruction result in some higher dimensions. The idea is that in algebraic geometry, you might try replace one of these Galois groups by a fundamental group. But you might say, well, if I'm in positive characteristic, what does it even mean to talk about a fundamental group? And so algebraic geometers will probably know about étoile pi 1, but I'll talk about it a little bit in a second. I just want to mention before kind of explaining the idea behind this, another reconstruction result that I find pretty surprising as well. So maybe someone can tell me why it should not be surprising. So I think originally this result was proven in the early 80s by Philip, and then generalized by Reconstruction. So I'll just state what was proven here, but there's a pretty beautiful generalization. So M and N will be smooth manifolds. Without boundaries, no other assumptions. And let's let P and Q be, well, integers bigger than or equal to 1 or possibly infinity. And what this result says is that diffeomorphism groups completely determine the manifold. So the result is if, let's say it this way, if I have an isomorphism between the CP diffeomorphism group of N, so I take P times differentiable functions from M to M, which have a P times differentiable inverse, to the CQ diffeomorphism group of N, so is a group isomorphism. And I don't put any sort of structure on these groups. They're just abstract groups. I don't try to make them infinite dimensional manifolds or anything like this. Then, in fact, P is equal to Q, and there exists a CP diffeomorphism that induces this isomorphism. So it's given just by transporting along this diffeomorphism. So if you know the diffeomorphism group of a manifold as an abstract group, you know the manifold, which yeah, I think is a pretty striking result as well. Okay, so that's just some motivation for the idea of a reconstruction result. And so are there any questions thus far? Yeah.
So when you were talking about this, you said that you want to generalize to higher dimensional varieties. What's the variety in this case?
Just the spectrum of the field.
Okay, rather than of the ring of integers?
Or, well, so it's just the spectrum of the field, but maybe it'll be clear later, yeah, how to extract this from the variety. But yeah, so it's like a zero-dimensional statement in some sense. Does that make sense? Any other questions? Okay, so I think for the next thing I want to write, it will be somewhat large, so I'm not going to use this board. So, yeah, there's a kind of issue in algebraic geometry, and yeah, by the way, I mean, I think to kind of get something out of this talk, you don't necessarily have to know a lot of algebraic geometry. I think that hopefully the things are formulated in a way that's kind of through analogies, so it won't be necessary to know all the details. But yeah, something you might be aware of if you've thought about algebraic geometry a bit is that the types of spaces that arise in algebraic geometry, well, we associate to a ring this spectrum, which is from like the perspective of manifold topology, a kind of weird topological space. It doesn't have very many like paths in it. So if you tried to work with some fundamental group in some naive way by saying, no, let's take this Zariski topological space and look at its fundamental group, that's a bad thing to do. So you have to do something else, which is called looking at the étale fundamental group. And I don't want to define this precisely, but just give you a kind of way of thinking about it, which in fact actually characterizes what it is. And maybe the thing to mention here is that in the Zariski topology, so the kind of standard topology you first encounter in algebraic geometry, something that's not true is like the inverse function. And so you want to make that true. And this is exactly what something called the étale topology is designed to do. But what I want to do is give you a kind of perspective on topological pi1, and then explain how it kind of translates to something in algebraic geometry. And then this will be our first shot at a replacement for this Galois group in this type of person. So this side will be about topological pi1. This side will be about this étale fundamental group. And so throughout this column, T will be a nice topological space. So if you want, think of a manifold or something like this. And I'll pick a point in T. We'll see how much space it needs. So well, the first bit of this will seem a little silly on this side. What is the fundamental group? It's a group. Okay, that's not very interesting, but the other side will be more interesting. And I want to maybe tell you about a theorem about the fundamental group, which is called the monodromy theorem. And so as long as T is connected, one thing that it says is any kind of notion you have of some kind of local bundle type object. So maybe the most familiar statement is that vector bundles with a flat connection on like a manifold are classified by something called their monodromy representation. So there's some data about pi1. Now, what the more general statement says is that locally constant sheaves of sets on T. These are the same things as sets with an action of this group. So how this works is, so yeah, I mean, if you're not familiar with sheaves, think of something like a vector bundle. So you have your sheaf, and you can take the stock at this point. So think of it as the fiber of a vector bundle over that point. And I mean, if you're thinking of it as a vector bundle, you can use parallel transport along a loop, and that gives an action of this here. Well, the way to say it in terms of sheaves is that every locally constant sheaf on the unit interval is actually constant. So if you have a loop and you pull it back to the unit interval, you get something that's constant. So it identifies both endpoints of the loop, and that defines your action of the loop. And that completely determines, that completely determines what locally constant sheaves are. Now, in trying to define a variant of the fundamental group for algebraic geometry, Grothendieck had this in mind. And so, I mean, there's some, I'm not going to explain how this is defined, but it's just something to look up if you're not familiar. So on this side, X will be a scheme. I mean, you can assume as nice as you want. And then X bar to X is what's called a geometric point. And the point here is that schemes, at each point, they have something called a residue field. And a geometric point is a choice of separable closure of a specific residue field. So in the case where this is the spectrum of a field, this is just a choice of separable closure of that field. And what this invariant is meant to generalize is Galois groups. So if I put a field here, I want to get a Galois group. So the Galois group, what type of thing is it? It's a profinite group. So that's more interesting. And this étal pi1 is defined in such a way that if I put in the spectrum of a field with respect to some separable closure, I recover as a topological group this Galois group. Okay. So that's nice. And there's also a theorem like this. So as long as X is connected, then there's a classification of locally constant étal sheaves on X. What does this mean? Well, it's not that important for this talk, but the point is you kind of cook up a definition of a covering space that behaves like they do in complex geometry, where you have the inverse function theorem. And there is some reasonable notion of things like vector bundles in this situation. And these, in the same way, are classified by, well, finite sets with a continuous action of this group. And it turns out that in this case, this is a characterizing property. This étal pi1, if you know what this side is, it's uniquely characterized by this property. Okay, so that's some abstract stuff. You might wonder something like, how does this compare to what happens like over the complex numbers?
Question.
Yeah.
Can you explain again how does this relate to the inverse function theorem?
Yeah, so what this side means, you have to define, well, the category of sheaves or some notion of covering spaces. And your notion of covering spaces, you define it to be such that the inverse function theorem holds.
Okay.
Basically, there are things that locally look like you have some kind of polynomial ring mod out by some collection of functions with invertible Jacobian.
Okay. So
but you have to define what you mean by covering space in this setting.
Is invertibility what you're looking for?
Yeah, invertibility of the Jacobian, basically. Yeah, that's a good question. Of course, yeah, I mean, one could spend weeks kind of explaining all of the details behind how this stuff works, but I just want to give some impression of what this invariant is like. Any other questions? Yeah.
Is there a reason that the finite set is up on the right where they?
Yeah. Yes, there is a reason, which I kind of swept under the rug here. Yeah, you want these things to have stocks that are finite sets. So basically the problem here is in algebraic geometry, like in topology, we have like universal covers. In algebraic geometry, these don't really exist. They only kind of finite covers exist, and you can take some limit over finite covers. So you always have to have some finiteness involved. And it has to do with, like, here, to make this type of theorem true, you need things like being locally simply connected. And that type of thing isn't true in algebraic geometry. And one way of kind of seeing that is because, okay, look at a point. If this thing's meant to generalize Galois groups, a point are like as local as you can get. And those, the pi1 of those is producing a Galois group, and that's usually not 0. So there's no local simple connectedness, but like kind of what happens is this type of result is always true if you put a bunch of finiteness hypotheses. So you just need that in algebraic geometry. Yeah, that's a good question. There's some technical details that I'll try to sweep under the rug, but I'm happy to answer if people ask or also after. Okay, so you might wonder what happens like if I'm some nice thing over the complex numbers where it makes sense to look at the complex points, and that's something that's, well, maybe singular manifold basically, and then I could take pi1 in the topological sense, and how does that compare? So this is the subject of a theorem called the Riemann existence theorem. So if you know some other formulation of the Riemann existence theorem, maybe it's a fun task to see why this is basically equivalent to this. So if you have x that's over the complex numbers and some technical assumption called finite type, then what you can do is the following. You can take the topological space that's, the solutions to the equations over the complex numbers, that, if we assume some smoothness, would really just be a smooth manifold, but it's something maybe slightly more general. And you could take, on the other hand, this a tall pi1 of x. And you might ask, are these the same? Well, this one is a profinite group. This one is just an ordinary group. It could be something like the integers, which is not profinite. So no, they're not quite the same, but there's a map like this, and it becomes an isomorphism after profinite completion. So there's a way to make any group into a profinite group that's basically saying, let's just record only the finite quotients of this group, and the finite quotients of these two groups are the same. So that actually often lets you compute what this is, because in many examples of, say, surfaces or kind of things that arise as solutions to systems of equations, you can compute these in topology, and then you just say, okay, I just do some formal procedure which lets me compute the more general. Okay, any questions about this? So the next section is then about some conjectures that people had about this. So the point is, this is a replacement for the fundamental group in topology. There's a whole very well-developed theory of this. It was originally developed by the Grothendieck school in like the 60s. This is how to think of it, but it won't really be necessary for this talk to have the precise definitions. So this third section is going to be on Abelian geometry. And this could also have been named Reconstruction from this pi1, but Grothendieck called it Abelian geometry, so I will too. So there's a conjecture that Grothendieck made in his 1983 letter to all things. And there's some interesting history here because this was like after the period where Grothendieck left math and then was kind of maybe trying to return to doing math. And I don't think he was aware of these kinds of results that I mentioned, like this Mostow-Prasad rigidity theorem. And he doesn't seem to be aware of this, but somehow he made conjectures along the same lines. So that to me is often a sign of something that's kind of interesting, where you can come from completely different areas and somehow arrive at the same type of ideas. So the conjecture is something very vague. So I'll state it this way. If X and Y are abelian varieties over these things that appeared in Pop's theorem, finitely generated fields of characteristic 0. Yeah, it's also, I think he was maybe not even necessarily aware of Neukirch and Uchida's work. I'm not 100% sure about that, but it's pretty interesting that he made this conjecture. Then isomorphisms from X to Y should be the same as these isomorphisms up to conjugation from this pi1 étal of X to pi1 étal of Y. Okay, so I put this word in quotes, abelian, and that's because even today, no one really knows what this means. So yeah, this is kind of a funny thing. And maybe the thing to say about this is that the issue is, well, maybe now I wish I had done this in the opposite order. If you remember this Mostow-Prasad rigidity theorem, part of the assumptions guaranteed that these spaces only had one homotopy group. Now you might ask, is there some like higher étal homotopy group? And it turns out the answer is yes. And like if you're in the complex case, you write the same formula, but you replace 1 by n. And so it would only be reasonable to make this kind of conjecture if there were no higher homotopy groups. So like that's a pretty restrictive assumption. And so, yeah. So yeah, the issue is that really you need to know at very least what k pi 1 is. So what it means to have homotopy groups in only 1 degree, and you know, it's not easy to come up with some geometric criterion that would guarantee this. So what I'll do next is I'll state one very striking result that is positive in this direction, and then I explain how you might get away from this issue of like not really knowing how to even formulate this conjecture. So there's been a lot of, there's been a lot of work in this area. Let me just highlight one conjecture that, or one result that is pretty striking. So, and we're getting closer to modern times. So there's a result of Tamagawa from 1997 that says, so let K and L be fields which are either finite, so some FQ, or one of these finitely generated fields of characteristic 0. So this meant you're some number field, and then you could have some function field variables. And X over K and Y over L, so they're not even obviously defined over the same field, affine hyperbolic curves. So this means in algebraic geometry, there's also a notion of Euler characteristic, and this means that the Euler characteristic is negative. Then he claims that this result is true. So isomorphisms of schemes from X to Y, those are actually the same as isomorphisms modulo conjugation of these fundamental groups. So again, we have a reconstruction result that says, you know, under maybe some pretty strict assumptions, if we're interested in these types of curves, they're completely determined by their fundamental groups. It's an algebraic invariant that completely determines them. And there's a lot of work in this area, namely by Shinichi Mochizuki. But you know, I won't say everything. This is just a kind of one result like this. But kind of the constant problem in this is exactly this issue that you have to assume super strong things, and you don't even know really what the assumption should be. Even like, I don't know, more, well, maybe this year is 30 years after, or 40 years after the conjecture was originally stated. So that's a bit of an unfortunate thing. So what I want to do next is talk about some recent reconstruction results that answer this question in a different way by saying, okay, let's replace this by something else that's a bit more complicated than a group, but is something not that much more complicated in a certain sense. And then we'll be able to ignore all of these kind of restrictive hypotheses and issues like this. Any questions before I do that? Okay. So I want to leave this up here because it will be useful in the thing that I'm going to say next. So yeah, this is kind of on some recent reconstruction results. And I'll talk about one of my results and hopefully if time, some other results that are also pretty interesting. So the results of mine, there'll be some joint work with Clark Barwick and Saul Glasman. And okay, so what I want to do is explain an example, or I will tell you a computation one could do if you had all of the definitions. and how that informs constructing a more refined invariant that will capture basically all of the information you could possibly imagine. So maybe the thing to say is in algebraic geometry, the most simple things are fields. They only have a point and these Galois groups. The second most simple things are things like discrete valuation rings, such as the p-adic. So I'll just do this for the p-adics, but what I'm about to say would work more generally. And yeah, the point there is you have the fraction field of this thing, and then also the residue field when you modify the maximal ideal. So there are kind of two fields and they're related in some way. So the example, which is a computation one can do if they know the definitions, but I'll just tell you, one of these objects appearing here in a tall sheaf on the spectrum of the p-adic integers, for example, that has two prime ideals, the maximal ideal and the zero, consists of the following things. It's a triple of data. So it's a V that's a continuous representation of, I can look at the field I get by modding out by P, that's FP. So it's a continuous representation of the Galois group of FP. There's another field I can get by taking the fraction field, so inverting P, and that's the QP, the p-adic rationals. So it consists of a second piece of data, which is a continuous representation of the Galois group of QP, which may be something kind of interesting if you're interested in working examples. We computed what this was earlier. This turns out to have an explicit generators and relations description. So one could make this example very explicit. And then you might wonder how, there has to be some data connecting these. And there's a way that these are related that might be familiar from if you study number theory. There's a group inside of this Galois group of QP, which I'll just abbreviate like this, called the decomposition group. And there's a further group inside of it called the inertia group. And the result is that you can obtain this group, well, not exactly from this group, but as a quotient like this. So there's an isomorphism from this subgroup below the smaller subgroup to the Galois group of the smaller field. So that's true anytime you have a discrete valuation ring, but I just wanted to make this seem more concrete. So what you might naturally put in this third column is like, if I have a continuous representation of one of these, the other one, and then there's some way to obtain the first one from the second one, what you might put, yes, is the natural thing. So a map, which is equivariant for the actions, well, I have something with this FP action. And from the thing with the action of the Galois group of QP, I can create something with an action of the Galois group of FP by taking the fixed points under this subgroup. And then that has a residual action by this quotient, which I'm identifying here. Okay, so you might imagine it's possible to create some sort of gadget that records kind of the Galois groups of each point of your scheme. And it records some data relating them like this. And that would completely determine this. So it's something like a quiver, but maybe a little bit more complicated. So that's basically what we did. So the theorem, which I'll state in a kind of rough formulation, but I'm happy to state it much more precisely. It just requires unpacking some things, is the following. So for X a scheme, we associated to it something called gal X, which is a category recording the Galois groups of residue fields and the ramification data relating them. So I'm happy to give a precise description of this at some later point for those who are interested, but let me not do it now. And the theorem about this object is a reconstruction theorem. So the result is if we have K one of these fields that appeared at the very beginning, which is a finitely generated field of characteristic 0, then this assignment, it's a complete invariant. Of, okay, normal, you can think being smooth case keys. But let me highlight what I mean really by this, which is something stronger than this isomorphism statement. It's not just that it detects isomorphisms, but it also detects all morphisms. So if you have homomorphism between these schemes, it's uniquely determined by something that happens with these categories. So it determines completely these schemes. So it's better than just detecting isomorphisms. And there are a number of applications of this result. It gives you a number of new tools that you can extract from this, where you can prove a lot of results, mainly in a tall homotopy theory, that either weren't known before or were known but had hard proofs, and the proofs become very easy with this access to this new invariant. So that's just one type of result, but the thing that I really want to highlight is that you don't just determine the isomorphism type, you get all morphisms as well. And maybe in the last 1 or 2 minutes, let me state a different result in this direction that I don't have anything to do with, but is kind of aesthetically similar. So, so this, by the way, I guess originally was from 2018, so something pretty recent. And the next thing I'm going to say is even more recent. So somehow recently there's been a lot of activity in this reconstruction area. So here's a sample theorem of Janos Kolar, Max Lieblich, Martin Olson, and Will-Sawin, that's also in this reconstruction area, but a little bit different. So yeah, here's one variant, but there's a ton of results that they said. So X and Y should be normal, so think smooth, projective, irreducible schemes over fields of characteristic 0. Then if the dimension of X is bigger than or equal to 4, then every homeomorphism, so there's an underlying topological space of the scheme, which I'll write with these bars. Every homeomorphism is induced by an isomorphism of schemes. So it says you have this underlying topological space, which if you look in low dimensions, it basically doesn't tell you anything. Like fields all have the same underlying topological space, it's 1 point. Discrete valuation rings all have the same underlying topological space, it's 2 points with a specific ordering on the points. One is open, one is closed. Curves also basically all have the same underlying topological space in algebraic geometry. But if you're in high enough dimensions, just the underlying topological space completely determines the isomorphism type of the scheme, which is also pretty striking. Now, you can't reconstruct morphisms like you can with this variant, which is invariant, which is a lot more complicated. But yeah, and maybe an interesting thing to think about is how these two things are related. And I think we don't really know, but I'll finish here.
Well, thank you very much. I have one question. What are your presentation skills? Because they really are excellent.
Oh, thanks. So one thing that I think was really fantastic was at MIT, I mean, I'd be interested in how things are done elsewhere because I don't have that much experience. But at MIT, one thing we had was these communication intensive classes in the major. And I think every major has to take 2 of them. And in particular, there's this math project class where you are made to do a lot of presentation, but there's also some like scientific writing lecturers who are part of this. And I think it was like incredibly helpful to take this class. And I don't know if other universities have this type of thing, but I thought it was like super, super useful.
I hope they would, because I think we've all attended presentations. I don't know, maybe early in my career, I gave some where the person might say, you know, this is really important work. I just wish that this person could tell us what they're doing. Anyway, but thank you very much for this. And do any of you have questions?
Can you give a little bit of intuition behind like why you need like a normal kind of assumption?
Yes. So there's a very good reason for this, which is okay. So you can take something like a cuspidal cubic, and this has a singularity. It's not normal. Maybe, yeah, it's not smooth. So if you think of normal as being very close to smooth, but there's a way of fixing this singularity. So why? You can resolve this singularity. This is what's called the normalization. So this is like an affine line. This is a cuspidal cubic, and this is a normalization. Now, maybe the thing to think about is, yeah, the residue fields of this A1 map isomorphically to the ones here. And there's a result called topological invariance that says the étale topology or even the Zariski topology, it can't tell the difference between these two things. So yeah, if you're trying to construct such an invariant, you know, out of that kind of data, you just can't tell the difference between these two things. And normality is basically, there's a precise thing called a universal homeomorphism, which is kind of exactly the things which the étale topology can't tell the difference between. And if you invert those in characteristic 0, that's essentially equivalent to normalization. It's something slightly more complicated called semi-normalization, but this is basically the best thing you could hope for. Yeah, that's a great question.
Other questions? Let's thank our speaker again.